Hi, my name is Anirban and I'm a PhD student in Computer Science Department, Rensselaer Polytechnic Institute. Today, I'll be talking about our paper, Performance Optimization for Edge Cloud Serverless Platforms via Dynamic Task Placement. This was accepted in CCGrid 2020. So first, let me start with a brief intro to edge computing. With the increase of use of intelligent edge devices by consumers and entities, there is a massive increase in the amount of data generated at the periphery of our communication networks, right? Now, edge computing paradigm helps leveraging this data by allowing computation to be performed at the edge of the network, which is both downstream from traditional cloud services and also upstream from the data producers. It therefore moves compute closer, allowing more sophisticated applications such as speech detection, sensor data stream analysis, autonomous cars, computational photography, and federated learning. As we see in the Gartner hype cycle on the right here, for technologies in 2019, Edge AI and Edge Analytics are at the peak of inflated expectations. So we expect the Edge AI and Edge Analytics to be somewhere around here for the current cycle of 2020-21. Now, as you have seen in the previous slide, there can be different kinds of workloads on the data is produced, such as face detection, autonomous cars, etc. However, there are many challenges to workloads on edge devices. Applications may need low latency response. The applications may need to use to meet a user specified deadline, or they may be subjected to different kinds of budgeting, such as cost budget, cost or energy budget, or even reduction of energy consumption. However, there are also some benefits to executing jobs at the edge, such as the low cost of execution, primarily because then you don't have to execute jobs in the cloud, which usually costs a lot of money. And at the same time, by not sending the raw data from the edge to upstream cloud, we end up saving a lot of bandwidth. Now, in such scenarios where the users have imposed a lot of constraints on the edge devices or the execution at the edge, for example, some cost budget or some latency constraint or some energy constraints, it may not be feasible to execute then all the jobs at the edge or the entire workload at the edge, in which case we may offload the jobs at a higher resource cloud. So what is cloud computing? So cloud computing has been there for quite a long time. It's not new, of course, we know about that. It provides the user an appearance of infinite resources and scalability. It allows the user to rent and pay for the use, and that's where the cost comes in. So essentially, it would allow you to have infinite resources with added costs. In this study, we considered the cloud as an offloading destination from the edge. Now, there can be different types of resource or units of resource allocation in the cloud, such as VMs in traditional infrastructure as a service, scenarios, containers, and serverless functions. In this study, we would use serverless functions for running compute on the public cloud. Now, in this context, let me give a brief overview on the related works that have been done so far. So, computational offloading has been studied with respect to VMs using either optimization problems or different kinds of greedy heuristics. Quite recently, we have also seen offloading of neural network computation, mostly by chopping it up into several parts and by running some of these parts in the edge and some of these parts in the cloud. With respect to serverless computing, scalability of platforms, some kind of benchmarks on function latencies, infrastructure retention, infrastructure provisioning, and how they behave have been studied. Several other studies look at reduction of SLO violation or efficient partition of function chains for reduction of cost or to maximize the resource utilization from the provider's perspective, etc. However, in our scenario, we are just looking at single-stage serverless functions and trying to optimize either the cost or latency from the user's perspective and not from the provider's perspective. Based on such a background, the following is our specific problem statement. Now, depending on a situation where we have a single edge device and the presence of a seemingly infinite capacity public cloud, where execution of jobs in the public cloud may incur additional cost, we must understand that depending on different resource constraints and different kinds of latency requirements, which are mostly user specified, may lead to infeasibility of executing all the jobs on the edge device. Now, when such a situation arises, we may consider leveraging the cloud as an offloading destination from the edge. This may incur additional costs. However, in this paper, we are looking at dynamic task placement between the edge and the cloud, and we consider two user specific criteria. As I mentioned, the first one is cost budget and the second one is latency deadline. Since we'll be using serverless computing as our workload execution paradigm for the rest of the paper, it makes sense to give a brief introduction here. So serverless computing is a relatively new computing paradigm. It's more of a programming paradigm than a physical paradigm actually. So it allows users to execute their stateless event trigger code without having to worry about maintaining the infrastructure. And function as a service is a type of serverless computing paradigm. It allows the user to generally run granular chunks of code in the form of functions and only pay for the CPU cycles used by those functions. So it's highly scalable because in the way in which these functions are deployed, you can have multiple versions of the same function running or multiple replicas of the same function running, and these replicas can scale up to many replicas when the incoming workload is higher. So there is high scalability, and the storage and the APIs are usually handled by the cloud provider. The user just have the option to configure CPU or the memory to modulate the amount of computing resources allocated to these function replicas. And the good thing is that this can be readily extended to the edge via different kinds of user provider libraries such as AWS Greengrass, which we'll be using in this paper and we'll see later on. To repeat, the following is our system model. We consider a single-stage serverless application, that is applications which consist of a single function, and these applications can execute either at the edge or in the public cloud. At the edge, we consider single edge device configuration, and the public cloud we have or may have multiple serverless function configurations for each function. And all of these functions can leverage parallelism in the public cloud because of this function scaling which is available, as I've mentioned in the previous slide. This figure shows our framework. The figure on the right, it shows our framework. This is a dynamic task placement framework. It consists of an edge device. All right, let me change the pointer. It consists of one edge device and cloud services. It can be different cloud services, not necessarily AWS. Now, the edge device contains our framework, which is a long-running service. It runs within a serverless function, and then it also can either execute the job. So there are several parts in this framework. The first one is a decision engine, which decides whether to execute the job entirely in the cloud or entirely at the edge. The decision engine is connected to a predictor. The predictor consists of several estimation modules, which I'll discuss in the next few slides, which allows us to predict the end-to-end latencies, cost, etc., based on which the decision engine makes the decision, right? Okay. So once the decision is made, then either the uploader module will upload the the raw files or the input data to the public cloud. The public cloud, these raw data is stored in a bucket, which will in turn trigger serverless functions, and the serverless functions will do the computation and store the results in public cloud. In case of edge-only pipelines, the edge device itself will execute the entire workload, and it will then upload only the results to the public cloud, and then this will get stored in the public cloud storage, or it may also be routed to other third-party applications available in the cloud. So one thing to note here is that both at the edge device and as well as in the cloud services, our execution happens inside serverless functions. So in our framework in this paper, we address two optimization problems to place tasks between the edge and the cloud. In optimization problem 1, we are trying to minimize the cost subjected to deadline per job delta, and in optimization problem 2, we want to minimize latency subjected to some budget per job. Now, the second optimization problem is a little bit different from the first optimization problem, because here we have a constant scaling factor alpha. So what alpha does is essentially allow us to accumulate the surplus or like unused budget. So if a job executes and doesn't use up all the budget, we'll accumulate the budget, which we can leverage to execute more jobs in the cloud later on if needed. So for efficient execution and task placement using optimization problems mentioned in the last slide, we need to have models for both end-to-end latencies TK and the end-to-end the total cost of executing the jobs in both the edge and the cloud pipelines. And in order to model these latencies, there are several elements we need to model. For example, the entire end-to-end latency of the cloud, it can be broken down into several constituents, such as the upload latency, the function start latency, the compute latency, the storage latency, etc. And the edge end-to-end latency can be similarly broken down. Now, once we know what the constituent parts are, we can then obtain some preliminary measurements by a pilot study, or like a preliminary study by executing these applications in these pipelines for some amount of iterations. And then once we have some numbers, then we can generate some latency estimation models. We see that most of the end-to-end latency constituents depends on file characteristics, such as the file size or the function configuration if the function is executing in the public cloud. On the right, we see some latency numbers. On the x-axis, we have characteristics of the files, and on the y-axis, we have latency. So the figure on the top, we have edge end-to-end latency, and the figure on the bottom, we have cloud end-to-end latency. We directly see that the cloud end-to-end latency is of higher variance than the edge end-to-end latency, of course, because then there are many more moving parts in the clouds, and the numbers will get out would be more grainy. However, in all these cases, there is a linear trend, and therefore we can use simple linear regression models such as ridge regression in order to get some estimation models. Now, focusing on the task placement framework on the left here, once we have all the estimation models for end-to-end latencies, we can put these models inside this predictor part. And now this decision engine, given an input, can query the predictor in order to know the end-to-end latency and the end-to-end cost for executing the job in the in the edge as well as in the public cloud. And once it has these numbers, then it can decide whether to execute the job using the cloud only pipeline or to execute the job on the edge device using the edge only pipeline. So the following is our experimental setup. In the edge setup, we are using AWS Greengrass 1.7, and as an edge device, we are using a Raspberry Pi 3B. And our Raspberry Pi is synced with a GPS clock in order for us to calculate the exact latency and the differences. In the cloud setup, we are using AWS Lambda to execute serverless functions in the cloud. We are using multiple memory configurations and which are deployed simultaneously for each function in the public cloud. As for the storage, we are using AWS S3. And the way in which it's configured is that once we upload an image to the AWS S3, it will trigger the corresponding Lambda function. So we'll have one AWS S3 bucket assigned to one function configuration of AWS Lambda respectively. And we are evaluating our application and our optimization problems using three applications. The first one is image resizing application. It just resizes image. The second one is face detection application. So given like a picture of a group of people, it will detect the number of faces in that image and save it in a text file, save the results in text file and the coordinates of the faces. And the third one is a normal speech to text, that is given a speech or audio file, it will translate the audio file into a text file. So we now consider the experimental results. We study the performance of our framework based on extensive simulations, and these are the results. The first result that we obtain is for minimizing costs. So this is the optimization problem 1 that I mentioned. Here we minimize cost subjected to some latency deadline per job. On the x-axis of all of these figures, we have increasing deadline per job, and on the y-axis we have the total cost. This is on the left y-axis, and on the right or the green bars, these represents the percentage of jobs which run at the edge out of the total number of jobs. we observe that different applications behave differently. For example, in the speech to text, which is the rightmost figure, as we increase the deadline per job, with increasing deadline, increasing number of jobs get executed at the edge. And since increasing number of jobs execute at the edge, the total amount of cost, both the actual and the predicted cost, goes down. However, the situation are a bit different in the other two applications. Next, we look at the second optimization problem, where we want to minimize the latency subjected to budget constraint. So on the x-axis, we increase alpha, which is the scaling factor that I mentioned a couple of slides back, which allows the user to modulate the amount of surplus a job can use in order to leverage its execution in the cloud services. Now, with increasing alpha, we see that the amount of budget remaining at the end of execution goes down, which is represented by the green bars. So it goes down in all the three cases. And also we see that with increasing alpha, the actual and the total predicted latency, end-to-end latency, also goes down, because with increasing alpha, more and more jobs can now be leveraged to be executed in the public cloud. And generally, executing jobs in the public cloud, at least in this scenario, since it's a single stage function, is much faster. We also see an interesting, because it's also parallel, we also see an interesting behavior in the speech to text, which is again like the rightmost, where as we increase alpha for 0.4, then the amount of budget remaining at the end of the execution becomes negative, which means that at the end of execution, we may end up using more budget than we originally intended to use. And so since this is a simulation, we can allow this to happen in order to see the variations in different executions. But however, in real life, we can set some sort of a check-in mechanism which will prevent subsequent jobs from being offloaded to the cloud once you use up the entire budget. But again, this would happen at the expense of latency. So in summary, we have here presented a framework for edge cloud dynamic task placement using serverless computing paradigm, both at the edge and at the cloud. Our approach is a data-driven approach based on real-world applications, and we show that accurate estimation of cost and average end-to-end latencies can be done using such framework, and then we can use these estimation models to do opportunistic offloading to public cloud, and therefore it's possible to optimize for both cost and latencies in single-stage serverless functions. Thank you.